How's it going, everyone? Eulier Gonzalez here. Today, let's go to now dive deep into this stuff known as the shape of a function, this particular concept that we're going to add out in our tool belt to, like when you wear some sunglasses, in this kind some special sunglasses, functional sunglasses, when you evaluate code, that when you apply this set of transformations and tools with the goal of make your code predictable. In other words, have a high degree of confidence that that particular piece of code work as expected. And then you can focus now on the things that really matters, which is the business logic. So this is a course taught by Kyle Simpson, and I think this is part of the advanced topic as a senior developers and the perhaps tech lead. All right. So the difference between a tech lead and a senior developer is that now a tech lead can hold the entire system on his head. That's the whole reason of this. And at some point, if you're going to build your own products or you're going to work with others, you eventually will get used to how things work. You know, what are the little cables that you need to plug in here and to wire them up and stuff like that. So as a senior developer right now, okay, that once you're able to understand this kind of stuff, you eventually going to provide value. So despite that you have never looked at a particular piece of code before, you at least understand how that things work, the inner mechanism, and then you can now provide a solution to that. So there's some certain levels here, so junior, mid-level, and senior, and a tech lead. So the junior is that he doesn't know the context, but he can do the task individually. However, a mid to senior level is that someone that at least has the known of what's going on, and now it can autonomous is make a task. Unlike the junior, where you need a lot of guidance, but a senior, he knows is the inner mechanism, and despite that she or he have never seen that code before, well, he can now provide that particular solution. So here we are. The TLDR of this video is to look at the shape of a function, which is a particular concept that as we now go into the functional programming, and then we started to apply that in our code base. This is a tool belt that we need to consider, and if you're going to use some functional programming libraries, or even when you write code or you read code, this is a stuff that is this is part of the convention that is good to know, that is good to have, and it's good to know. Now, so the goal of this course is, as we put it here, right, is that learn and apply the functional concepts and tool sets that will give us is a high level of confidence in our code, so we can ship more faster and we can now improve and fix and debug the code much better. So yeah, we first talk about is the introduction here, of how do we get here, but what we really care in today's video is this argument pointers so far. Now, so in the introduction we make at least a case to present ourselves that why you should go with functional programming. And as I mentioned before, the whole point of this is that since the vast majority of the time we now write our code in an imperative way, which is telling the machine all of this set of instructions, all of this set of rules, Now, here, the idea is to, well, follow certain practice of the functional programming, but is to make that particular functionality, make it predictable. Now, this is not only the value proposition of that, but also is to make the code readable. So make the code readable, which it turns out to be much more easy to maintain, fix, and debug, right? Now, because initially we're gonna see is, or the way how it's been taught by other authors, according to Kyle Simpson, is, well, most of them they tell you is from top to bottom, right? So all this particular approach, when you talk about, when they teach you that kind of stuff, is quite hard to grasp on, especially if you need at least some practical stuff here. And Kyle Simpson, well, thanks to him for creating this particular book called Functional Light JavaScript, is to, hey, let's go into now, with what we already know, starting to incrementally move the needle to the functional programming. So it's more a hands-on approach. It's more a using what we know to move forward, and I really love that approach. It's actually building on stuff that we have previously know. And also there is some learning curve when it comes to at least learn this functional pattern, right? So in terms of readability and in terms of the shift in your mindset between the imperative and the declarative, right? As you can see here, right? So this will improve readability, and this is now the change between one to another. All right, until you fall in the pit of despair. I was quite a couple of days ago, weeks ago, I was in that pit of despair or valley of despair because I didn't know what I was doing. And also I was working for Banco de Chile, which is a Chilean bank. That's the like the Federal Reserve, all right. Of course, I'm working for an offshore company that provides now subsidiary services to Banco de Chile. So in any case, but the point here is with that is, well, look at all of these particular concepts that we're gonna see and apply that. Right. Okay. So again, this is just repeating a little more that we know. The code is provable. Let's read the code, and that we can now focus our attentions on learning these mathematical foundations. Pretty much like when you, when you go out in a restaurant, so you take out your girl, and then you pay the bill, you know, or you go out with your family and then you want to now split the bill. Now, what happening is that you don't need to know the mathematical foundations of the arithmetic or these basic operations, addition, subtraction, multiplications, and divisions, or how this mathematical proof, or why 2 plus 2 is equal 4. You know, you just only know that this is a tool that you want to use, and therefore move on with your life. And this is a kind of exactly the approach that we're going to look at this. And that's why we're starting by looking at what is a function here. So by learning all of this set of tools, the idea is, and I know I'm quite repeating myself, bear with me, But the idea here is that let's going to learn all of these mathematical foundations, so then we can now focus on the business logics, since most of those codes that use those mathematical principles, we can rest assured that they will work as expected. So it gives us predictability here. So we can focus on things that are not, right? So for that, that's what we need to look at, the function purity. So function purity, or looking at this difference between the function and the procedure. A function is something that must return something, all right? And as a way to make this code provable, there are also certain stuff that needs to be done, certain guarantees, certain rules that we need to make that happen. And that is that not only that our function and the semantic of this function must reflect is the inputs and it is computed output. Okay, what is the relationship between that? Which is something that is this, the semantic relationship between the input and the computed output, but also is additional rules to guarantee that this code is provable. So those kind of rule is that that function must not cause side effects. In other words, stuff that at some point it will alter the state out of the function scope. But this is inevitable, because at some point, if you are a developer, you need to talk to your database or any input and output. If you're reading the local database, or you're reading external database, or network calls, and that kind of stuff. So the idea here is to avoid side effects with function calls. What does it mean? This is that anytime you are not only defining the function, if you are responsible for designing that function, but also is to, anytime you're gonna call that function per se must not alter the state of the application in other points. So it must do that stuff. So one single input, one single output, the same input, the same output. So yeah, this is part of the side effect that I mentioned before, that we can run into it. Also DOM manipulations, timestamp, random numbers, or anything that cause CPU hit, because at some point you need to wait for the computation to be completed, or CPU time delay, right? So to make that happen, to create a pure function, is that the variables or the parameters that we are receiving, and there's a sort of difference between parameters and arguments, we're going to talk about that later, but the parameters that we are receiving, or the arguments that we are receiving here, in this case is the first is a pure function, and the second is another impure function, because at some point we are now taking is an external state, and we don't have certainty of what is the outcome of these functions. However, if we expand a little bit the scope of this, and we say, hey, but what will happen that only our functions start from this, okay, that this is the entire file, all right, that only is going to run this particular set of instructions, okay, and the question will be, if you do this at another function, and if we define the restriction that, hey, this will be now this file, and we can make sure that C is a const, it won't change, okay, can we say that add another is a function here? It's a pure function? So not only that, is that with var variable is add another function is still a pure function. So the answer is for this scope, yes. And that's what happened with the context here. So the point of this function purity is that if we're able to reduce the reassignment surface that can happen, it will of course give us much more confident about this code. That's why this particular technique of returning a function of another function of another function of another function like that here is saying, hey, let's sorry is saying, hey, let's go to now is take each take the relevant parameters and then pass to another functions and then pass to another functions. So the whole point of this is to reduce is the reassignment surface. Why is this? Because if you do that at some point, so now it will introduce some sort of uncertainty. So this is a particular technique that functional programmers are actually using. So they return a function of another function and of another function, blah 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 blah, yada yada yada. That's quite interesting. Absolutely. That's quite absolutely interesting, and it's because this particular pattern. All right. So anytime you see that in your code, you say, oh, the goal of this is to reduce the surface area of reassign this value, and therefore give us much more confident that this function will return an expected output. And also, well, as I mentioned before, the same input and same output. Now, what happens when we cannot extract? What happens when in a function, at some point, we have a function or a procedure that is not pure, okay? Because at the end of the day, function purity is just say, hey, we're sure that this code will work as expected. That's all. So we have high level of confidence of that. But what happens when your function, especially your function's call, because function purity is focused on that, on function call, not only definition, is on function call, right? So by the time that you call this function, you're gonna get the expected behavior. But what happens when you can create or can define this function purity? How can you now extract the impurity of this function? All right, and there are several techniques to that. One of them is the extracting the impurity by now is taking the lexical scope and then return with the new state. All right, which is something that we are quite common in React. It's like, hey, let's go to take now the previous snapshot here, or let's gonna take is the lexical scope here, create a new variable, and then let that variable have access to our side effect functions, which is perhaps is trying to modify is the local variable, the global variable at some point, or is talking to a database or waiting for something to complete, you know. But how can we extract that? Is by now, well, is taking the lexical scope, create a copy of that, and then pass. So take the outer lexical scope, all right. Create a copy of that, so you have now a new reference that is going to be, well, give you the new state out of that and return it. So this is something that we went through this, especially with this particular technique. containing impurity here. So for example, like this. If you want to see a little bit more this code, review code space, view file, that's right. So here we just globally creating is a data structure, an array of students that as a way to now make this function here, the source student, that is modifying is the global scope. In other words, doing a side effect. Okay. Well, the point here is to take now that lexical scope where these functions alter that state, recreate this new one in this function scope, so now it can be reused by the time that you call it here, right? So this is quite interesting because here we effectively are also creating is a closure. All right, that's mind blowing as well. You know, that's also mind blowing because here we're working is with reference. So far so good. Now the other technique, which is more like a brute force approach, is to do that via adapters. In other words, that take this snapshot, which is this, is that take the current snapshot of everything that function needs to, and then restore it like this, and then restore it. Most of the times, what we have looked is the previous technique, which is containing the lexical scope, and therefore return a new copy of that. All right. This is also perhaps another one that you might use, that takes snapshot of everything and then restore it afterwards. Okay. That also might works. So with that, all right. Now let's go to focus on what we really care about which is argument adapters. And here we are. And here we are. So why this is important? Because let's take a look at something. So I want to bring your attention to this topic because it's relevant as you starting to understand and apply the next coming concepts to make our code provable, and that is the argument adapters. In other words, to understand that the function's arguments at the end of the day, even though that people use that interchangeably or interchangeable, but there are technical differences. So parameters and arguments. So parameters are the name at least in the computer science, here in the JavaScript. So is the name, so parameters are the name inputs from the function definitions point of view. So in other words, so x is a parameter, xg is a parameter from the function definition. Now the other is argument is the value that we pass when we call the function. And this is something quite important to understand, right? Or at least have a be crystal clear of this, right? So parameters are the name inputs from the function definition point of view, and the arguments are the values that we pass when we call the function. Okay, so why this is important? Because functional programmers call this is the shape of the function. And we're going to talk about the shape of the functions in terms of going with a more technical concept that functional programmers go with, which is the type signatures. All right. So type signatures are what is the shape of a function, and the shape of a function is to be more in plain text or in plain English is the number of arguments, the number of parameters, and the shape of those parameters that we pass in and that we get it afterward. Okay, so that's what the functional shape is the number of parameters that we pass here. Okay, so there is a formal way to describe the shape of a function, or there is a formal way to describe the shape of a function over here called type signatures. Okay, aka the number and the kind of things that you pass in. Okay, so the number and kind of thing that you pass in, and the number and kind of things that you get out of it, or that come out of it. So in this case, it's X and G. So far, so good. And functional programmers are obsessed with the shape of the functions for a good reason, because they want to now see how to fit, pretty much like a Lego block, how these functions fit with another function, how this piece of Lego block fit with another, and so on and so forth, right? So you can build your own spacecraft ship, for example, or your own Millennium Falcon in Lego, or your Eiffel Tower. But that's the point here. Now, this is what functional programming describe about the functions arguments, the argument and the type, and also the function shape or type signature. So for that, all right, the functional programming tends to love is unity functions, or the next level, or in the next kind of favorite functions functional programming love is a binary function. But again, this is quite interesting because the shape of this, all right, and they say unity or binary function is that it refers in terms of the arguments. Okay, so now how these arguments are gonna be passed is the way how they define the unity here, or the binary. So this is very interesting stuff about to talk of the shape of a function, the argument that this function is going to receive, right? Because now when we need to, for example, go with other type of functions, when we need to make this function fit with another function, the question is that how can we make that possible here? How can we make sure that, for example, these particular functions with one or two arguments, okay, fit with this another function with one single argument when we call it, okay? That's why it's important to describe is the argument and the parameters. So parameters are the name inputs from the function definition point of view, okay? An argument is the value that we pass when we call the function. So by having here is these two functions, all right? This is a good example here, all right? Is that, hey, I'm taking this function function one, and function binary. But the point here is that how you can fit now a unity function that's going to return is one single output to match now the type signature with the shape of a function to a binary, right? So we need some sort of adapter here. And this is a particular concept from design pattern, all right? Like this, all right? The adapter is a structural pattern, all right? Because we are actually modifying is the structure of this. So we need is as an adapter, all right? That's what we're going to explore in today's video. Let's get into this.
We can also adapt the shape of functions. And this is where we're going to really start to push your thinking around functional programming. Because we're going to introduce a concept. I'm sure many of you have heard this before and maybe just didn't fully connect with what it meant. Have you heard the term before, higher order function? Sometimes it's abbreviated HOF, H-O-F. Okay? So what is a HOF? It sounds much more complicated than it actually is. Okay? That's the cool part, is that when we uncover these meanings, a lot of this stuff is actually pretty intuitive. Okay? Not always, but some of it anyway. So what is a higher order function? Well, put simply, a higher order function is a function that either receives as its inputs one or more functions, or returns one or more functions. That is, if the values going in or the values coming out are functions, then that thing itself is the higher order function. So a thing that doesn't receive functions, we would call it a single order function. And if it receives functions or returns them, we call it a higher order function. If functions, we would call it a single order function. And if it receives functions or returns them, we call it a higher order function.
Mm-hmm.
Or returns one or more functions. That is, if the values going in or the values coming out are functions, then that thing itself is the higher order function. So a thing that doesn't receive functions, we would call it a single order function. And if it receives functions or returns them, we call it a higher order function.
So if a function receive its arguments,
we would call it, the values going in or the values coming out are functions, then that thing itself is the higher order function. So a thing that doesn't receive functions, we would call it.
Exactly. So a function that doesn't receive a function that doesn't receive a function that doesn't receive a function as argument, okay? So a function that doesn't receive a function as argument, we call them single order function. But again, this is from the mathematical approach, bro. A function that receive
a single order function, and if it receives functions or returns them, we call it.
Exactly. A function that receive or return a function, we call them high order functions. So far so good. I was quite familiar with that concept. Perhaps not with the single order function, because if a function doesn't receive a function or return a function, that's a high order function, a single order function. But now here we talk about a high order function.
But a higher order function. Okay? So right on line 1, we see a utility that I've now called unary. You see that it receives a function denoted by the parameter fn, and it returns another function back called 1 in this case. That's called a higher order function. The unary utility here is a higher order.
So unary and binary here are high order functions.
Function. What is it doing? Well, it's kind of interesting because
So unary and binary here are high order functions.
Because that one function that gets returned back, it only has one named parameter. You may or may not be aware that in JavaScript, all functions are what we call variadic, meaning it doesn't matter how many parameters are declared, you can pass as many arguments or as few as you want. You can define a function that expects 3 and you can pass 4 to it. You can define a function that expects 3 and only pass 1 to it. JavaScript's not going to say, you're doing something wrong. You can define a function that expects 3 and you can pass 4 to it. You can define a function that expects 3 and only pass 1 to it. JavaScript's not going to say, you're doing something wrong. They're variadic functions. So if I were to take a function that might expect 4 and pass it, like, for example, the f from line 13, one that expects multiples, it's an n-ary function. But if I pass it to unary, what I get back, line 17, g is a new function, which has the name 1 that we see there on line 2. G, down on line 20, when we pass in 4 inputs, how many inputs actually make it to the underlying function? 1 that was an n-ary function. But if I pass it to unary, what I get back, line 17, g is a new function, which has the name 1 that we see there on line 2. G, down on line 20, when we pass in 4 inputs, how many inputs actually make it to the underlying function?
Only 1. Yeah, only 1.
How many?
Yeah. So when we call unity, okay. So when we call unity, all right. So when we call unity with a function called f, italic. No, come on, for real. Okay, when we call, so when we call unity with a function f, like this. So when we call unity with a function f, so when we call unity with a function f, exactly. So when we call unity with a function f that's going to return the number of arguments, is interesting. Okay, the number of arguments here. So when we call the unity function with f, that we're gonna return the number of arguments. How many arguments here? How many arguments are exactly? With how many arguments? With how many arguments? Like this. Yep. With how many arguments can we, yeah, with how many arguments can we call? Okay, with how many arguments unity function will call? And that is here. So you say, hey, because now you're passing me a function, and unity function is a higher order function that say, hey, I'm going to execute that function, but with one argument, or the function 2, all right, with 2 arguments. So this is how you can now shape, or this is how you can filter is the number of arguments that this function, or to adapt the function of arguments that this function will receive. So far so good, right?
Because on line 2 we name just a single parameter arg. So in other words, we took a function whose shape was to be n-ary, and we reduced its shape, we restricted its shape, such that it is what?
Unity.
It's unary. That's what the unary utility does. It's a higher order function that adapts the shape of a function to be unary. We'll see use cases throughout the lecture and exercise where that kind of thing will be useful. But I want you to get more comfortable with the idea that a function of one shape can be adapted to have a different shape. That's critical. And that's a key takeaway from this higher order functions pattern, is that we can take any function and adapt its shape. And that's critical when we have 2 Lego pieces that don't fit, and we need to sort of make them fit. We got to make an adapter so that they fit. And that's what these utilities do. In fact, virtually all the utilities that you'll find in whichever functional programming library you choose to use, RAM, Dil, Dash, whatever, whichever one you pick, all of the utilities are these kinds of higher order functions. Almost all of them do this kind of thing. They take a single function in, they do something, make a new function that does something different, has a different shape. So you're going to see this kind of pattern all over the place. And what's critical is your takeaway at this moment is that this is line 1 through 5 is not some sort of higher black magic kind of coding. It should feel very tractable, very sensible to you. Okay, I can see I take a function and make another function wrapped around it. And that's the key, because you as a functional programmer have to get comfortable with making your own higher order functions. Not just using the result of a higher order function that's provided to you, but making your own. When you see that I have this piece and they don't fit, the functional programmer says, I can see what kind of adapter I need between them, and I make myself a utility to do that. And then I create the shape-adjusted adapter. Make sense? So unary makes the G what we call the unary of F. Line 18 we call H equals the binary of F. So on line 21 when you see H receiving 4 arguments, the underlying function, the F function, only receives 2 of them. We've made it the binary. If you haven't dealt with higher order functions before, expect for that brain to feel a little, but this is critical. It's going to be core and central to all of your future functional programming. Let's look at some other kinds of adapters. Here's one called flip. It will sometimes be the case that you have a function, let's say you have a binary function, and it receives an x and a y. I don't know what it does, it doesn't matter. It's a function that receives an x and a y. And there's a bunch of places where that works just fine. But then there's this other place where you need a function that receives them in a different order. You need like yx. For whatever reason, you need to be able to provide the arguments in a different order. That's a new shape adaptation, right? And if it's a shape adaptation, then we can make an adapter do that. And we call that adapter flip. Notice what flip does. It takes in a function, returns back a flip function, line 2. It lists arg1 and arg2, and then it transposes them when it calls the underlying function on line 3. And everything else that's passed, if anything, is passed along untouched. But flip simply flips the first 2. By the way, flip is the name that is canonically used in most libraries for exactly this function. It's called flip. Same with unary and binary. Wherever possible, I'm going to try to use whatever names you'll probably see out in the wild. Not always, but where possible. Okay? So you'll find a flip in there, and now you know what that does. And that's like learning about the plus operation in math. Because now that you know what that does, every time you see flip with an fn passed in, you know that the thing that's being passed back has transposed the 2 arguments. And the job of becoming a functional programmer is getting comfortable with seeing all of these different mathematical pieces and saying, yep, this is the flip, and yep, this is the unary, and yep, this is the binary, and this is this, and this is the that. Seeing those and recognizing those at a glance and using them just like you use 1 + 1 = 2. When I make G on line 11, that is the flip of F. So when I pass in G 1, 2, 3, 4, the underlying F actually receives 2, 1, 3, 4. The first two arguments having been transposed. A somewhat less common example that you may find would be reverse Rs. That's a name that I made up. Okay? Because this isn't one that you're going to find in all of your functional programming libraries, but it's one that I've often found useful. So I went and made my own higher order function utility, because sometimes I have like an n-ary function, 3 inputs, and I need all 3 reversed, not just the first 2 flipped, but I need all 3 of them go in reverse order. That's happened to me on a number of occasions. So what does reverse args do? Exactly what you expect. Takes a function and returns back a new function that takes the list of arguments line 2, and line 3 it reverses them. That's an example of an adapter that I made that I might use. Not one you necessarily find, but it's an example when you find yourself messing around with the shape of your functions and they don't fit. Try to figure out, number one, can I change the shape of my function at definition so that it fits better? If not, can I make an adapter that changes the shape? Everywhere that we do this, we're looking for common patterns. The functional programmer is looking for the Lego piece that looks exactly like the Lego piece that they have a big old pile of. I want this thing to look like a Lego piece that I already have. I don't want to go invent new utilities all day, every day. Stop and think about that for a moment, because that may not be obvious. Why might I not want to just invent ad hoc utilities all over the place?
Because you
quite honestly, it's kind of creative fun to do so. I can come up with all kinds of different shape-changing ones. Why wouldn't that be a good way of
but there's
approaching
no convention.
And I would suggest to you that
diversity is
important. It's because the whole
to explore,
point
but convention
is
for
the
collaboration.
familiarity, the recognition of it. Wherever possible, if the things that we're using are the known common things that every functional programmer for the last 60-something years have used, that's good. But when a functional programmer comes to your code base and they see this thing and they're like, what? I've never seen that Lego before. It's less familiar. So somebody has to spend more time reasoning about that math. Where it's possible for us to do so, we should try to make it recognizable at a glance. We should try to use the standard common ones. So that means get real familiar with at least one functional programming library and most of the methods that it provides. Once you've spent a few hours reading through the documentation for Lambda, for example, you're going to find yourself looking at a thing, seeing this shape and saying, oh, I know what that one's called. I saw that in the Lambda docs. Congratulations, that's functional programming. Instead of going venture your own and make one that isn't consistent and familiar, try to make it fit in with the existing patterns where possible. And when you can't, make your own. Document them well, put them in a standard library that the whole app uses, and use them as much as possible. That way everybody gets familiar with them. Another example of shape adaptation that we commonly do. You will see this much more often than may be obvious at this moment. One kind of shape adaptation is I have a function that takes individual arguments, but I want to call that function with an array. It's expecting individual arguments, but here I have an array. What do I do? How do I get all the contents of this array into the individual arguments? Some of you may know about JavaScript's .apply method, which takes an array and spreads the values out as arguments. And there's a reason why that utility is called .apply, because that's what functional programmers call it. When you take an array and spread it out as individual arguments, that's called an apply. Here I've called it spread args, just so you knew exactly what it's doing. It's spreading the array of arguments out into individual ones. See how?
Okay, spreading but this is about the arguments here, and the shape of the function. Specifically of the things in terms of the arguments. In terms of what are the things that this function would receive, and what is the number of stuff and shape that this function will take, and the number of stuff and shape that will come out of it. And then we are playing is now with the arguments here. And how now by creating some sort of arguments, some sort of adapters, functions to play with.
How it does line 3, the ... that's the spread operator. It is spreading out an array of arguments into individuals. But that's exactly what JavaScript's .apply does, and it turns out the name for this utility, as you'll find it in almost all functional programming libraries, is apply. So the apply, G is the apply of F, line 11. It's the spread args that is the apply of F. So when I call G with an array, F gets individual arguments. Everybody follow me? Here's a little pop quiz. We're not going to actually show this code, but I just want you to play with this in your head, maybe type it in your code for just a moment. This is a pop quiz. If spread args is a function that can take an array and spread it out into individual ones, what's the inverse of that? What would unspread args look like? Unapply, what would that look like? I would be able to pass in individual arguments, and the underlying function would receive what? An array.
An array. That will be like.
Just think about that for just a moment. We'll just take like 30 seconds. That's the pop quiz I want you to think about. Look at that spread args and think, how would I change this to do the inverse? Spread it out and involve G with an array. F gets individual arguments. Everybody follow me? Here's a little pop quiz. We're not going to actually show this code, but I just want you to play with this in your head, maybe type it in your code for just a moment. This is a pop quiz operator on line 3. We simply need to move it from line 3 to line 2. We need to, as complex as you might have thought, the dot 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 operator on line 3. We simply need to move it from line 3 to line 2. We need to gather the arguments from line 2 and pass them as a single array line 3. That's it. That's the only difference between a spread args and a gather args, or an apply and an unapply, is whether we gather first and then pass the array, or spread and then, or take an array and then.
Exactly. We get so with the spread we say we take all of these arguments and then we spread create an array, or we take an array and then we spread that all of that. That's interesting. So you have now a spread here. Nth argument. It is nth argument. Holy shit. Oh crap. That's interesting. But I don't think this has been quite applied this to. Land Castleway clone deep. Assign in, and then sequence. in Haskell. Holy F, bro. I get it. I get it. I get it. Holy elf in Haskell. Jesus. Any way, bro.
That's present. It's the only difference between the two. And you'll find apply and unapply in all your favorite functional programming libraries. All right, so let's take a look at another aspect of functions. And this is kind of a higher level concept, and it may twist your brain a little bit, but that's okay. That's what we're here for. We want to push ourselves. So stick with me on this. Point free. What is that? I've heard this phrase many, many times when I was trying to kind of pick up functional programming, and it sounded like one of those fancy concepts that I didn't know what to do and didn't know what that meant. But then I learned about it, I was like, oh, well, I've kind of already been doing some of that. And that's one of the gratifying sort of takeaways from a lot of functional programming is that it turns out that this big idea of functional programming is built up by a bunch of tiny little things, most of which we've already done, or at least we can find intuitive. It's rarely the case where you look at something and say, that is just so completely out of the realm of anything I ever would have thought or done that it just totally mind bends. It's the combination of all those things that really pushes us into this different paradigm. So we're going to talk about this style of writing our functions. And this may sound a little strange, but it's a way of defining a function without actually writing anything in the function. It's a way of making a function by making it with other functions. That's really what point-free style is about. So what does this even mean? What does that name even mean? Well, I don't know if any of you remember this. I have a very vague recollection back to my, 7th, 8th, 9th grade time frame, something like that, a long time ago. I remember a teacher saying something to the effect of fixed point functions, sometime when we were doing something with our graphing calculators or something. And I don't remember what they meant by that. I have since Googled it, looked it up on Wikipedia, and I sort of now come to a better understanding. I wish they just said at the time more clearly, or I'd been able to understand more clearly what it was. But the idea of a fixed point function, remember back to our initial example, we were talking about, we were motivating at the beginning of the course, the f of x and the 2x squared plus 3. Remember that function? Well, the idea there is that the input x become, outputs a y. What if that function had multiple inputs? What if it took an x and a y and it outputted a z? Well, now we'd have like a three-dimensional, it would be a two-dimensional surface in three-dimensional space, right? The idea of a fixed function is that if you have more than one input, you take one of the inputs and fix it at a certain value. So for example, I could say, take a function that takes an x and a y and produces a z, and fix the x at the number 3, for whatever reason. Now that's going to tell me the line on that surface at exactly x equals 3. That's mathematically what that was all about. So fixed point functions were where we took one of the inputs and we fixed it at a certain value. Well, that sort of speaks to why we're calling this point-free, because point-free definition is defining a function without needing to define its points, aka its inputs.
Its inputs.
Without needing to explicitly define and map its inputs, can we define a function? And in a sense, it really ends up as a class or a family of techniques for defining functions by way of other functions. Okay? So let's take a look. Some of you have probably done something like this. Many of you have passed in a callback, for example, like to this getPerson utility. I pass in this callback that receives line 1 an input called person, and it passes that along to some other function, in this case to renderPerson. Anybody seen code like this before? Seems somewhat familiar. Okay? So this is very, very common. We receive inputs in one callback, we pass that input to another callback. That person parameter there is the point, it is the input, in mathematical terms it's called a point, for the onPerson function. And you notice that we define the onPerson function by specific the input. It's very common. We receive inputs in one callback, we pass that input to another callback. That person parameter there is the point, it is the input, in mathematical terms it's called a point, for the onPerson function. And you notice that we define the onPerson function by specifically and explicitly listing out that
arguments free.
So what if we could define the equivalent of that
and
function
the call points
without
in the
needing to
functional
list the
programming
point at all?
Of
Some of you may have actually done this before. This is where, when I was first learning point-free, I was like, oh, I've done that before. I just didn't know that was called point-free. You might notice that the onPerson function taking a single input and the renderPerson taking a single input, you might notice that they have basically the same shape. which means if they have the same shape, then they're interchangeable, which means that I could just pass render person as the callback. Anybody ever done something like that before, where you have this wrapper function and realize, oh, I don't need the wrapper, I can just pass in the function? Well, if you've done that before, I have good news for you. Without you even knowing, you were doing this really, really cool thing that I'm going to give you this term, and you're going to be able to go back to your teams and use this term, and you're going to sound really smart. And everybody's going to be like, whoa, that's really cool. What you were doing was called equational reasoning. That sounds cool, doesn't it?
Okay.
I'd like to put that on my business card. I'm an equational reasoning master. It sounds cool. It's actually pretty mundane. Okay? What's mundane about it is that we're basically saying, if I have this thing that's got this one shape, and I have this other thing that has the same shape, even if they do different things, if they have the same shape, then they're interchangeable. Equational reasoning means reason about this thing and say that it is equationally, not equal like an identity sense, but equal shape sense. With this other. Here we have an on-person function that is equationally is equivalent to the render person function, which means that we can pass render person. And the takeaway here is that we were able to get away with defining the function without needing to list the point. That's one aspect of the point free, but I said it's kind of a family of techniques. So there are other things involved that fall into this heading of point free. And before I even show you some of these other more advanced techniques, I just want to warn you, it's like what I talked about in the intro to the course when I said that you'll be trying something and all of a sudden you'll cross this line from, oh, I was tracking with you to, like, what did he just do, right? At some point in the next slide or two, we're going to cross that line for all of you. It's okay. We definitely did for me as well, okay? Before I even show you, though, what I want to warn you is if you see this and then you say, as a response, well, I don't get that. That's not more readable. That's weirder to me, so I'm not going to do it. That's not the best response. A better response would be, wow, that's not what I was expecting. And it's going to take some time to get used to that. I should try that a bunch more. Okay? But on the other hand, another response, and I have seen this from folks, including myself, is that you see this and you're like, whoa, that's so cool. I'm going to do that everywhere. I'm just going to like point free everything. And you very quickly explode the complexity, the surface area of that complexity, way beyond your capacity to even understand what it is you've written. So that's also not a great, healthy response. The healthy response here is to push yourself a little bit, but fall back to things that are practical for you. And then push yourself a little bit more and fall back to what's comfortable and practical and readable and reasonable. And do that little by little by little.
Like hit the gym.
What I'm about to show you is the first time I saw it, I was like, oh, I don't know about that. And then after a while, that became comfortable, and then my line moved a little bit. And then I tried a few more and more advanced techniques in point free, and my line moved a little bit. And then I tried a bit more, and a few months later, the line moved a little bit. So that's the way it's going to be for you. And particularly with point free, don't go overboard. Don't go overboard with it, because this is that point where my readability curve started tanking. It was with point free. I was trying it because it was so cool, and I way overblew the complexity of it and lost all the benefits. At the end of the day, if your code is not more readable and understandable, then it's not benefiting. So what we want to do is we want to get to that idea of the shapes being equal with each other. Here I have an is-odd function. It's pretty straightforward. It uses the modulo operator. So any value, modulo 2, if it returns us 1, that means it was an odd number. If it returns 0, it's even. Okay? Very basic math concept there. But if I wanted to find the is-even function, there's a couple of ways that I could have done it. I could have said is-even, and on line 6 I could have said v mod 2 equals 0. And that would work just fine. It's mathematically accurate to say that is-even is v mod 2 equal to 0. But I did it a little differently. I defined is-even in terms of the is-odd function. And specifically, I negated it. Because we have a binary here, something that's either even or odd. It's not both, and it's not neither. It's either, a number is either even or it's odd. So I'm asking the question here, if I take this is-even function and I define it in terms of is-odd, as opposed to doing just v mod 2 equals 0, what have I purchased with that choice? What benefit am I getting from defining is-even in terms of is-odd? And the answer I would say is, I have created a more visible relationship between the two functions. I have said that is-even is the negation of is-odd. Whereas if I just done v mod 2 equals 0, that relationship would exist, but it would be completely non-obvious. Here I am attempting to make it more obvious the relationship between is odd and is even by defining one in terms of the other. So it's not just about saving keystrokes. A lot of times you hear people say, why, blah, 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 dry, don't repeat yourself, right? That might be why a lot of people would justify, oh, dry, don't repeat yourself. I'm not saying that there isn't benefit there. Being unnecessarily repetitive can sometimes hamper the readability of a program. But actually, it turns out, sometimes in functional programming, it is better to be repetitive. So we don't want to take dry as like a religious artifact, like, oh, I have to have every single thing written only once, and everything is using the generic whatever. That's not always the best. Here, we're not doing is even in terms of is odd because we want to save a few characters of the modulo operator. We're doing it because we want to make it obvious that there's a relationship, a negation relationship between the two. And by thinking that way, we actually got ourselves 90% of the way to being able to answer this question, which is, could I define the is even function in a point-free way? Could I define it in terms of is odd without having to list out that v that's being passed in? Because there's the point. This is a pointed definition, and we're asking, could I define it point-free? Before I even show you how to do the point-free, we probably should have motivated what is the point of point-free? Like, what are we buying? Well, what we're doing is we're moving to that declarative style. When we have points, what we have is an imperative style that routes data from an input to an input. But when we use point-free style, we have a declarative thing. Here's a strange phenomenon that I've seen with the idea between imperative and declarative. Because the words themselves, the physical letters in those words, to me imply that imperative would be implicit, since the words seem the same, but it turns out that it's reversed. It turns out that imperative code is generally more explicit, and declarative code is generally more implicit. Now, if you stop 100 software developers somewhere, and you ask them the question, is it better for code to be explicit or implicit? 99 out of 100 are going to tell you it's better to be explicit. And what we're actually suggesting here is that in some senses, it's better to be implicit. It's better to be declarative and allow the existing Lego pieces that are in our application, either in the language or in our libraries, to handle those unnecessary details. Because it's not important for the reader of this code to see V on line 5 being passed on line 6. That is an unnecessary detail. If I can define this in a point-free way, I free up the reader to glance at and realize, oh, okay, is even is the negation is odd. So how are we going to accomplish that? If you can agree with me that it is beneficial from a readability perspective, how are we going to accomplish it? Well, we're going to accomplish it by creating a utility that adapts the shape of a function. Exactly like we did before with Haas, we're going to make another Hoff. Actually, we don't need to invent one. One already exists. I'm just going to tell you about it. Let's think about a Hoff, a higher-order function called not. This is, by the way, often referred to as complement in functional programming libraries. I don't like that name. That confuses me. So I like to use not. Sometimes I use negate. Sometimes I use not. I almost never use complement. But anyway, if you're looking it up, you'll find it's called complement for something like random. But what it does, it takes the function fn line 1, it makes a new function that's negated line 2, and all it does is call the original underlying function with all the inputs and return the outputs. But it does line 3, that little exclamation mark, it negates it. So now, when I declare is even, I simply call this higher order function utility not, and I pass in is odd. And what I would argue is not only is line 11 less to read and mentally juggle, because I don't need to see the function, calling another function, and passing the parameter, but it is even more clear the relationship between is odd and is even now, right? You can very clearly see
exactly.
that
It's
is odd
more
is the
easier.
negation, that is even is the
The
negation is
relationship
odd.
here is this. Is even is equal
That's
to
where we
not
get the
is
readability
odd.
gains in functional programming, and specifically in point-free style. Define one function in terms of another, you make the relationship between them much more clear.
You make the
You allow
relationship
the
between
how,
much more
the
clear.
imperative details to be implicitly hidden through a declarative style of code. That's the big takeaway from all the functional programming. You can almost stop right here and just get that, and you've gotten a huge nugget of wisdom out of functional programming. That's
You get much
the key
more.
idea.
You are more declarative.
All right, let's do an exercise to practice. So what we want to do is we want to get name. That confuses me, so I like to use not. Something like random. But what it does, it takes the function fn line 1, it makes a new function that's negated line 2, and all it does is call the original underlying function with all the inputs and return the
these
output.
functions and the other.
But it does line
Not
3,
is odd.
that little exclamation mark, it negates it. So now when I
higher
declare
function
is even,
that it takes the
I
function
simply call this
and,
higher order function utility not, and I pass
now
it
takes
off.
all of its arguments.
And what I would argue is not only is line 11 less to read and mentally juggle, because I don't need to see the function, calling another function, and passing the parameter, but it is even more clear the relationship between is odd and is even now, right? You can very clearly see that is odd is the negation, that is even is the negation of is odd. That's where we get the readability gains in functional programming, and specifically in point-free style. You define one function in terms of another, you make the relationship between them much more clear. You allow the how, the imperative details, to be implicitly hidden through a declarative style of coding. That's the big takeaway from all of functional programming. You can almost stop right here and just get that, and you've got a huge nugget of wisdom out of functional programming. That's the key idea.
It's because it makes more
The negation, that is
clear.
even is the negation is odd.
It makes much more clear about
That's
that.
where we get the readability
The
gains in
relationship.
functional programming, specifically in point-free style. You define one function in terms of another, you make the relationship between them much more clear. You allow the how, the imperative details, to be implicitly hidden through a declarative style of code. That's the
But
big
that's the
takeaway
entire
from all
here
functional
things.
programming.
It's
You
like
can almost stop
making
right
the
here
relationship
and just
clear
get that,
about
and you've
that.
got a huge nugget of
Make the
wisdom out of
relationship
functional
clear
programming. That's
about it.
the key idea. All right, let's.
That's all right. So, well, that'll be all for the video. Take care. Bye bye.